Sorry, some interruptions. So work. W1 to 2. Okay. W1 to 2. So 1 is here, the initial state. 2 is here, the final. Okay. So now I can write this again. It's the same thing. Q. This has some bitter sense, maybe. That's okay. Q1 to 2. Also, I can add this 1 to 2 to W as well. W1, but E1 and E2. Okay. E1 and E2 will be more standard. Okay, good. And actually E1 is U1, internal energy levels. So we will be learning on that as well. Okay, good. Little more explanation to go. If the gas entity mass is M, okay, in a closed system, M remains. M remains. Okay, M remains. I'll make this a little bit big maybe. No. Good. Then this is for the entire mass entity, gas entity M. So what I can do is I divide both sides because I need to go for 1 unit mass, maybe 1 kg. So U2 divided by. So this can be written as so E1 divided by M. We can write this as, follow me, small letters, small w, w, small q. Okay, this one. And is equal to E2 by M means per unit mass. This is just E2. Okay, interesting. Okay, just E2. So this one also you can write same. U1, simple, W. So you know that these are specific values means per unit mass. U2. Big U2 by M means small U2. So that is for 1 kg. Okay. Quite interesting. Okay. And if I take, say, if you have 1 kg here, 1 mass. One mass. The first law. This is E, small w, small q, small a. Okay. E1 plus W plus Q is E2. So, in a better way, what is this? Okay. So work is mole W. Q is small q. This is for 1 unit mass, 1 kg. This is your E1. This is your E2. Okay. So that's how it is. Also, you can write in U terms as well. So this may be helpful for you to understand the first law of thermodynamics expressions for closed system. So 111 means it's a closed system with a moving boundary here, possible. And there are this nature of applications as well. Okay, good. And even you can write this this way as well. You don't need 1, 2 even. Because we know it. Just put Q during 1, 2 process, heat interaction. So W, the work interaction. Anywhere you can keep it. You don't need 1 to even, because generally we can understand. But as a statement, putting 1, 2 is okay, but not putting also okay, but you can specify this is the work received by this gas entity when it changed from 1 to 2. Okay. Then again you can write this way. So no need W. 1 to 2, just Q is enough. Okay, more simplified. Whatever it is understood. Okay. Q1 plus W1 plus Q is U2. That's it. Oh, this way. Same. Okay. Yes. I believe it is okay. For you. Just some little clarifications. A very little one. But yes, work done. The PV change, we should come back to that again. This PV change, how we explain this W. How we explain this W. Yes. So we will come to this now. Very interesting. this one. What happens to the gas entity? When receives W? You know this, but you may need further clarifications. When receives W. Okay, when receives W. So I changed this question to this way. So let's say instead of W, I'm thinking if I receive a very small work done, tiny one, okay? So I will say when receives delta W, what happens, okay? A very small work done. So this is here. So this receives, okay, let's say when delivers, done. So work done. So when delivers, delta W. So delivers delta W. Sorry. Please be patient. This is one. Because we know that when delivers, something like gas volume becomes big. We know that. So this delivers W. Expands. Work W. So this is the question. So instead of the entire W, I'm thinking of maybe in a little shorter time, maybe in a millisecond. So this is, so this W receives maybe This takes, let's say, 10 seconds. So this delta W may be in 0.1 second, something like that. So we call this elemental level thinking. Okay. So elemental level thinking. Elemental level. Like elements. Maybe delta W may be 1% of W, example. Or maybe 0.1% of W. A tiny fraction when receives. So initial here, of course, when this delivers. So this is exactly the same here. Maybe a little increase. A little increase. So there is a work done. Yes. What? Delta W. What delta W? So this what delta W delivers this change like this. Okay. So this change is something like that. A little increase in volume. Okay, little increase in volume. So now taking the pressure here P, volume is V. Okay. Yeah, you can send the attendance. It's okay. Maybe. So for this little W, how this PV response is, P has no much change, but V has a little change. What change? V becomes a little increase. A tiny increase in V. We call it delta. V becomes V plus delta V. What is this delta V? Is the expansion. Okay. Delta V is the expansion because of delta W. That is what the effect on this. Okay, so this delta W is the expansion. Sorry, delta V. Very interesting. Delta V is the expansion of the gas entity. So I don't write the gas entity. And P has no much response for this case. It's so tiny that pressure has no much sensitivity, but we change. And what happens is this delta W becomes, you can show that, P times delta V. Okay. This delta W is equivalent to P times delta V. Means expansion times pressure become the work done. Okay. Expansion times pressure becomes work done. Understand? Expansion times pressure. So we are evaluating because pressure also going to get changed. So at this elemental work done in this tiny time slot, okay, time slot, let's say, time at delta W at little times delta T time. So this is what we can say, okay. Delta W is P delta V, okay. So delta means it is something like it's a tiniest, okay, tiniest change of parameter, even work done. Here the delta W is the smallest, is the tiniest contribution for this W, this delta W. So now, again, sorry. Elemental level thinking. Today maybe little. When gas receives actually when gas receives, this volume becomes little small. Sure, it's a little small. So plus delta V, that's true. But this delta V is a minus value. Okay. The delta V, actually it is a minus one. Because it shrunk. Okay. So anyway, we will see. So the work done. Work is delta W. So this delta V is a negative expansion. It's a contraction. Okay. So delta W, we can express as P delta. Delta V has a negative value. Okay, good. So sign conventions, later we will discuss. So anyway, expansion, but here it is negative. I put within bracket because it's a contraction. Because in compression, you know that there is a shrinkage. Now, I will bring this. Anyway, let me take the entire one. Yes. This compression, okay, tiniest change of delta V. I take this. I look for this tiniest change. Maybe expansion, positive or negative. I will take a tiniest change. See how I take it. Somewhere here. Tiniest change. Interesting. Yeah. So I take it to here because I have P here. Yes. This is general V. Use here. Sorry. Yes. Very nice. Expanding. Turbine. Expanding. So you have a P value here and a delta V. So let me take delta V from here. Here is delta V. Okay, here is delta V. And here you can see P. So P times delta V is the area here. Okay, area here. Yes, very nice. So P, the value here, delta V here. So P times delta V is delta W. Area is delta W. Interesting. So if you can evaluate, here you can see under the curve, there can be, okay, let me take a slide. See the nearby. You can see this nature of tiny delta V strips resembles underneath the curve PV. Okay, underneath the curve PV. Some, see, it's very difficult to draw. See further. Some, see. Likewise, area under the PV curve. From 1 to 2. All together. Okay. For each and every delta V, you have corresponding values of P. Yes. So this is how, if you know the tiny effect, you can evaluate if you know this PV behavior. Okay. Before you take this, you should understand what work done means. So work done for this little delta W is P delta V, means the pressure times the expansion reflects work done. Pressure times expansion. But pressure changes while experiencing expansion, this gas entity. So you have no constant pressure, but for tiny expansions, there are corresponding pressure rises or pressure decreases or pressure changes. So P times delta V, you can evaluate. So the primary factor is if there is a work done, there is an increase in volume, or if there is a receiving of work by the gas, there is a shrinkage of volume. Shrinkage, but of course, when there is a heating, it's a different story, but there is a corresponding shrinkage-like effect if there is a work done. Okay, that is very important. Work done is there, there is a change of volume. So this is how we are evaluating. So I will bring this here. Delta W is P delta V. Then W, what is W total? Is sum of all delta W, sum. So we add delta W, this every strip here. P delta V we calculate. Okay. Sum. Summation sigma delta W. That is sum of P delta V. You know this phenomena. Okay. Not to say phenomena, the principle of the way we can evaluate this. Interesting. Okay. So energized gas expands. So the gas will be experiencing a work done. You can witness it. So from 1 to 2, sigma 1 to 2. So from 1 to 2. 1 to 2 is maybe somewhere 1 to 2. Yeah, we have got 1 to 2. I add it here. 1 to 2. Okay. Start from the point V1 there, V1, V1. Okay, good. So I think you have some little understanding on this, a little concept. Hope you can understand. And also, I need to pay you attention to some of previous works not done for you. But for the semester, the B1 batch, I've done a session there. We have done very good study. Learning out of this. Displacing environment, and we have learned a lot of that. If I need to share that presentation, let me share with you. Not this one, this is your one. This one. So we learned about flow works. Very nice. So we have that some wonderful knowledge about enthalpies, entropies, flow works. So many things. This is a 4-hour lecture. Even we have analyzed this very well. We discussed this with the B1 students. lot of things. So for our lecture, I have uploaded this video because this went on very nice ways, and you can learn about entropies, about the internal energies and the flow works very well. It's a great help if you can go through this. If you can go through this, it's a great help so that I can, how to say, I can go through that in short period of time, and your knowledge will be somewhat coming in better shape. Okay. But for B1, I didn't do this part, but I did some basic for them to sense thermodynamics, because thermodynamics is not maths, even it's not English. It's a very nice subject. So thermodynamics, we should understand, we should have a sense of this uniqueness of this subject. So I got a lot of examples and all, because they are B1 students, most of them are from A levels. But anyway, those explanations seems very nice. So we came across a lot of thermodynamic phenomena in very comfortable ways. If you can go through, it is wonderful, because we learn about flow work as well. So this concept's all very nice. So today what we have done is, yes, we start from here. Receiving work by gas entity or working fluid, or delivering work. The PV change we are experiencing. And then we have experienced this, the receiving work, the energy level rising in this gas entity, and this is the closed system. And when there are heat interactions and work interactions both, so then energy balance involve both work, heat, and the initial and final energy quantities. So that's what all says. And finally, per unit mass, the specific figures, we derive some expressions for 1 unit kilograms mole. So it's very nice. The internal energies, work and heat interactions came as an equations based on the first law of thermodynamics, we call energy balance. So after that, we have to look into W. What this W is. W makes the gas, the working fluid, experience some volume changes. Then for tiny work inputs or elemental level approach, in the continuous work done of W, we take a tiny portion of delta W, and what experiences this gas, and we have noticed that the change of the volume from V to delta V plus means addition or a change. With P, no much of sensitivity for this tiny delta W. And finally, this expansion related elemental work done at pressure P, we identified as P delta V. You take the unit, P delta V unit is joule. Okay, P delta V. It is very interesting. Then even receiving work, also delta V, it's a negative expansion, but I just put expansion, negative. Then connect your previous day knowledge. So how make use of this? Seeing delta W in this PV graph as a tiny strip, representing the area as P delta V, which is delta W. And using of that, many P delta V's means finally the entire area underneath represents the work done during this expansion process. V change, and there is delta W for initially high work done, finally less work done. Of course, bigger volumes, but lesser p-values. So you can see the areas less, high areas. So always high pressure expansion produce more work. You can see out from here. That's why high pressure leading to high temperatures. Later we will see PVT connectivity. That may be the next day lesson. So I'm reminding you, I think I have emailed this to you. Please go through this. Thermodynamics is a wonderful subject and you have to put some time and effort for this, to understand this, to realize this subject, to do something useful, to take some good initiatives, to practice this subject. Practice again. Okay, to provide solutions, to initiate solutions. Okay, so that is very important. So we will see how the subject goes, and this is daily note. So I'm emailing this, and one-time note, you have it. So this will be helpful for you to connect this together. You have some solid thermodynamics background. Don't worry, little analysis, but doesn't mean it needs maths. Even maths is a kind of a language. It needs understanding. You have to understand math and you have to use it. Okay. Yeah. It is not for solving maths problems. Understanding and use it appropriately. That is not a big deal. Okay. So thermal science, technology, thermal engineering. As I mentioned, this is a very valuable, very expensive field. If you know this subject to the fullest, you will be valued and your service will be expensive. In return, you may have a bit of pay, and you have jobs everywhere. Because this subject is not physically seen. You have to use all the while your mind to see the things. That is very important. So here you have delta V. This is different delta V, but here I take small delta V's. Okay. So let me take this. See, stop sharing here first. I will take the daily note. Here, this delta V I take out. So, work done by gas during expansion. I just put as average pressure times V2 minus V1, that is relevant. Okay. So, delta V is a tiny delta V I take. Okay, good. So PA is the average pressure. Okay. Okay, good. So I save all the attendance. So all the three batches here, mechatronics, manufacturing, and BST. But make sure it's your responsibility to understand this subject. Okay. So your attendance matters. It's very important, and the real time Learning takes place when you are there on the Zoom and I'm here sharing the knowledge. So if you miss this, you will miss the subject. That's what I can say. You can avoid, you can miss the class, but you are missing a lot because you may not find this in the web, okay? Because we are sharing some experience and the way we are saying this. So you have to receive this and you receive some knowledge out of this and then you may have your own understanding. It's different. So collectively, we can provide the solutions. That's how it is. So attendance is quite important and it is encouraging, attending the class is encouraging. So that is very important. So if you miss this, because this is not the conventional doing of the textbook, so you may miss the opportunities, of course. If you don't attend and if you don't understand the daily note, it is very tough for you to pass thermodynamics. It is very tough for you to pass thermodynamics. So attending the lessons very important. So it's like that. So don't avoid. Okay. Magarina magarina. Ek system. So you may lose the opportunity. So don't purposefully miss the lessons because you will lose something. Yeah. So again, I want to remind you that if possible, just go through that video. I think that is a 4-hour one. You can see this picture, the balloon picture there. So you will understand a lot. And finally, we will take thermodynamics into our fingertips. Not in the books, but in our fingertips. So we are ready to do the things in big ways. So thanks for joining the class, Mutala. That's all for today. See you next week and please go through that video. 4-hour one, but would be helpful. Unedited one. It's unedited. Don't worry about the quality, but if you put an effort and some attention, you will gain something massive. So that is very important. So that's all. Take care, all of you. COVID is around still. So a responsibility to be safe. And see you next week. So wish you all good luck and bye for now. See you next week. Okay, Bhutala. I'm going to stop the class.
Thank you, sir.
Thank you, sir.
Thank you very much, sir.
Thank
Thank
you.
you, sir.
Okay, bye.